Okay. Here, let me give you something to...
Whoa! Almost right off the camera. Before we go into that, speaking of the integrating over high mass, when we originally wrote down that Lagrangian, do you remember we say we can neglect the derivative term?
Yeah.
We have that -1/2 d mu d. I think it was no, it was d.
Yeah, I'm going to do that again.
Alpha. Did you? I remember there was a question of whether or not we could do that, or for what.
Yeah. And in class, in class, the question didn't occur to me. I mean, when I wrote the notes, the question didn't occur to me. When I was in class, the question occurred to me, and I didn't immediately have an answer. Now I can give you an answer.
Okay.
So, let's just start with this action. So, big M squared, M is huge. So psi could be a complex scalar, it could be a fermion. Now, the point is that M is much greater than the scale of experimentally accessible, and by the way, you should try to pay attention to my ideas, but not to my spelling. So I'm not sure how many C's there are, and I don't know if this is an A or an I. Does anybody know for sure?
As long as you don't write 3, it's okay.
Huh?
As long as you don't write C3s, it's all right.
Oh, I know. Energies. Okay, so the idea is that we can do experiments these days up to energies of, center of mass energies of around 14 TeV at the European Collider in CERN. So the scale of experimentally accessible physics is of the order of 14 TeV. And so let me just write that down, 14 TeV. So what we're imagining here is that these are terms that are appropriate to physics at not 14 TeV, well, they also, not so much 14 TeV, but maybe 14 PeV. In other words, at energies 1,000 times or 1,000,000 times higher than 14 TeV. And so in this what we want to do then is see what is the effect of these terms, the main effect of these terms on the scale of experimentally accessible energies. And so that means that we neglect fluctuations. We're looking at things that we're integrating over Fourier components that are much higher than the scale of 14 TeV. So in particular, we're going to ignore the derivatives, or effectively, we're doing our path integral over fields whose Fourier components are of the order of 14 TeV, maybe 100 TeV or less, but not zillions of TeV. And at that point, then, we're ignoring those derivatives. So we focus on the effect of this Lagrangian. And now what we do is we complete the square. And so we write this as -1/2 m² phi minus G over M squared psi bar psi squared. So the cross term gives us this, but we have to cancel the quartic term that occurs from that. And so what we do is we add in plus G squared over 2M squared psi bar psi squared. So that cancels. So now this is just an equality. This is equal to that. Now when we do the path integral over phi, we can shift phi to phi plus G over M squared psi bar psi. So that's equivalent to path integrating. Oh, and then when we do the phi integration, it's just a Gaussian that gives us a factor out in front that's independent of other fields in the theory. It's just a field-independent thing involving m raised to some power. And consequently, the only effect on the low-energy theory is to have a new interaction, which is just G squared over 2M squared psi bar psi squared. So that basically is it. We're integrating over these high-frequency fields, and what we have left is this term here. The analogous thing for a gauge boson is to imagine we have something like this, minus a half m squared ya plus ig psi bar gamma a psi ya. Again, this is appropriate at huge energies, and I've dropped the derivative terms already. So I have minus a half m squared ya minus ig over m squared psi bar gamma a psi ya minus ig over m squared psi bar gamma a psi. And now the compensating term is minus g squared over 2m squared psi bar gamma a psi bar gamma lower a psi. And now we do the integration over the heavy gauge field just by shifting that gauge field. And when we shift the gauge field, we just get the path integral over y. In other words, the shifted thing, let me maybe make this clearer. So that's what we have left after the shift, and then when we integrate over the y's, they're not coupled to anything else, so this just gives us a constant factor out in front, and the effect is that we have a new term in the theory, and the new term is minus g squared over 2m squared psi bar gamma a psi bar gamma a psi. Now, you may notice, those of you who had a course in the weak interactions, that the Fermi Lagrangian for the weak interactions is something like G Fermi psi bar, and it's gamma a 1, and I think it's 1 plus gamma 5 in the notation I'm using. The effect of gamma 5 in Weinberg's notation is this, and when you take 1 plus gamma 5, what you do is you project out, you keep these the upper components and you lose the lower components. And so that means that this is a theory in which only the upper components of the Dirac field psi contribute. And this is the theory of the weak interactions that Fermi put forward in 1934. And
So
anyway, this procedure was introduced by Weinberg in 1979, actually. And yeah.
Sorry, that was just kind of fast. What are these Y fields?
Excuse me?
What are these, like, Y fields?
These are gauge bosons in a theory that is appropriate at the scale of grand unification, or the Planck scale, or the scale of 1,000 TeV, or a million TeV.
Yeah. And then,
So let's remember that the grand unification is like 10 to the 16th GeV, which is 10 to the 13th TeV. And the accessible energies now are 10 TeV. So we've got 12 orders of magnitude where there can be other theories. And it's been fashionable now for something like 40 years to suppose that there's nothing interesting happening between 10 TeV and 10 to the 13th TeV. Glashow called it the Grand Desert. And the reason for this is that if you look at how the coupling constants evolve under, you remember last semester we did a sort of fast discussion of the renormalization group. And so what happens as you go up in energy is that the fine structure for the strong interactions goes down like this. The one for the weak interactions goes down more slowly, and the one for U1 goes up for a while and then unifies and then goes down. And the question is, do these guys actually when it really does do this? I don't know quite how it goes. And the question was, do they unify? Well, they sort of unify, but and the place where they sort of unify is around 10 to the 15 or 10 to the 16 GeV. And so people said, well, that's grand unification. That was back in the 70s, and then there was a prediction made of proton decay, and so experiments were done to look for proton decay. And what they found was neutrino oscillations. Because they're huge, they're huge containers of water in which they were looking for protons to decay. They had all kinds of scintillation counters on the walls of the container, and they could see signals from neutrinos going through, but there was never a sign of proton decay.
Okay, and then, sorry, so then we get this effective Lagrangian from that, and then what was the connection to this LF? This LF you're calling it what?
Connection to one?
This LF, you're saying this LF is like the weak interaction Lagrangian or something?
Right, F is Fermi.
Yeah, LF is Fermi. And
Right,
so it's only one,
right.
it's only one part of it,
This
right?
is the structure of the Fermi.
Okay.
And although I have to admit that things are a little bit different, because it's something like an E here and a nu there, and when Fermi did it, it was something like a proton here and a neutron there. That's what they were thinking of.
Okay.
But in more modern language, you'd make these quark fields, and the actual theory is the one we're going to be talking about later today. In any event, Weinberg in 1979 wrote a paper on this. I'd be grateful if somebody would tell me what the reference is. I found a reference to a paper by him in Physica, but I don't know if that's the correct journal. And that's a journal owned by Elsevier, and Elsevier, that corporation is not interested in science at all. They're just interested in making money from libraries, and so they haven't preserved in any decent form any of the papers. So if you ask for a paper from 1979, you get something that somebody photographed. Somebody made a Xerox copy or something of it, and that's all they have, and they really don't care about anything else. Whereas if you ask the physical review for a paper from 1929, you get a copy that is perfect. So that's the difference. I urge you in your professional lives to avoid sending anything to Elsevier. Instead, try to send things to real organizations run by scientists such as the American Institute of Physics or one of the American Chemical Society, some academic optics organization. All right, now, so now I want to get back to the Higgs mechanism and so forth, and I thought I would just add something that try to make something a little bit clearer. Last time, if we just go back to the abelian Higgs mechanism, then what I said was we could write a field B sub A as A sub A plus 1 over m dA of sigma 2. And if we do that, well, first of all, F mu nu, or FAB, is unchanged because dA AB minus dB AA is the same thing as dA dB minus dB BA. So there's no change there when you add. In other words, the derivative of sigma 2 is like a gauge transformation on the electromagnetic field. And so consequently, if you write the Lagrangian in the form minus a quarter, FAB minus a half m squared dA, so BABA. And then, if you actually just take the Lagrangian that we were talking about as the Lagrangian of the model, but use BA instead of AA, then what you get is minus a half dA sigma 1 minus m squared sigma 1 squared plus cubic and higher terms, so cubic and quartic and a constant. So the Lagrangian becomes exactly the Lagrangian for a massive vector field and a scalar field of mass m. And then you get the cubic and quartic terms. So this is in the class notes. I rewrote the class notes. These class notes are called masses.pdf, and the link is something about notes on spontaneous symmetry breaking on the class webpage. And so I think this is nice. This is a nice way of thinking about it. And all right, so let me skip that. I did a little more about the SON Higgs model, and I don't know how much I should just much I should. Oh, all right, I'll do a little bit of this. Let me just remind you of what it is. It's a quarter trace FIK, minus a half dA phi transpose dA phi plus a half m squared phi squared minus lambda over 4 phi squared squared. And here, of course, Fik is the commutator of di with dk. So this is diak minus dk ai plus the commutator of ai with ak. And here I'm writing the gauge field here as E tor, or the tor here is IT. So T is Hermitian and tor is real and anti-symmetric. The Hermitian ones are imaginary and anti-symmetric. And you can define these generators for this F index is you can think of as two integers, row and column. So tau RC sub IK is delta RI delta C K minus delta R K delta CI. So in other words, in a particular row you put, and a particular column, you put a 1 here and then you put a -1 in the symmetric place. Those are the generators. And then you can compute trace of tor RC tor R prime C prime, and this is just -2 delta R prime delta C C prime. And so this parameter K is parameter K is -2, yes. I should have. K is the thing where you say trace of TA, TB is K delta AB. So the K here is -2. And it's because these generators are real and anti-symmetric. And so the easiest way to think about the mass generation of the mass matrix for the gauge fields is to say that this field phi in the vacuum takes a value phi 0 with a 1 in the top component and 0 everywhere else. And then what you find is that, so I'm skipping some stuff here, in the vacuum the kinetic Lagrangian, that is this thing, these terms give you -1/2 E squared phi 0 squared course, yeah, all right. E squared phi 0 squared tor RC 1I tor R prime C prime 1I ARCA A R prime C prime A.
Can I ask you a quick Yeah, so I'm a little confused. Why does tau have 4 indices? I mean, I can get why it would have
Well, the
3.
bottom 2 indices are the row and column of the matrix
Yeah.
Tor. The
Yeah.
2 upper indices label which generator,
So you have 2 indices
to label the generator.
Okay, why are you using 2?
Well, because it's very easy to construct them if you say you need 2 indices to specify where you put the 1.
Oh,
Say it's row 2 and column 5.
so a lot of them will just be 0.
What? Oh, everything else is 0, yeah.
Almost all of them are just 0.
Everything is 0 except for, it has to be, you put a 1 in a particular place,
Yeah.
and then it has to be anti-symmetric, so you put a -1 in the corresponding place. And, let's see, what else? I was going to say something else. This also tells you how many generators there are, because they're anti-symmetric, so there are zeros on this diagonal.
Sure.
And so you have n-1 this way, and so it's n-1, n-2 over 2. I'm hesitating for a moment because this doesn't give me enough generators for the case of n equals 3.
Wait, you have n-1, then you want to sum from 1 to n-1. So shouldn't it be...
I want 3 for the 3 by 3
Should it
case.
be
I
n
want
times n-1 by 2? The sum of all...
Oh, the answer's wrong. It's
You need 8
It's
for
n-1 over 2.
Mhm. Yeah, that's the sum of integers from 1
From-
to n-1.
From 1 to n-1.
Yeah.
That's right. Okay, anyway, that gives us the answer. And so that's how many generators you have. And then if you compute this thing using these generators, what happens is, because of all the delta functions, what you get is just a 1/2, a sum, c equals 2 to n, e squared pi 0 squared, a 1c a 1c a. So in other words, what you get is n-1 massive gauge bosons. And quite a few left massless. And the ones left massless are n-1, n-2 over 2. And that, of course, is the number of, that's the number of generators that annihilate this vector. And that's because they're the generators that not only have zeros here, but also have zeros here. And by anti-symmetry also have zeros there. So they're just ones here. And so that's a sum from 1 to n-2. These annihilate the phi zero, so those correspond to, that's also how many gauge boson, those guys also, let's see, yeah, the number of Goldstone bosons that might have, the number of would-be Goldstone bosons is n-1. So would-be Goldstone bosons. But those Goldstone bosons make these n-1 gauge bosons massive. And then one gauge boson is massless. So one is massless. And one boson, scalar boson, is massive. So for the SON Higgs mechanism, you wind up with one massive scalar boson, n-1 massive gauge bosons, and n minus 1, n minus 2 over 2 massless gauge bosons. So quite a few massless gauge bosons. So generically, this Higgs mechanism does not make all of the gauge bosons massive.
I have one small question about the notation.
All right, hold on. I haven't given you. Wait a minute. I have to give you some candy.
Just one is fine. No. Okay, that's cool. Thanks. Yeah. Yeah. So.
All right, let me get a sweet coffee.
Go for it.
I was just gonna ask this subscript on these taus in your LK file. Is that tau Li or is that tau 1I?
1I.
Oh, thanks.
And the 1 is because
Thanks.
you see, what you had here was a vector phi 0, which is 1, 0, 0, 0. And then over here you have 1, 0, 0, 0. And then you have the covariant derivatives. And so the Tor matrices you can call this a tau I1, and that differs just by a minus sign.
Yeah.
In fact, I use that too. Anyway, you've got to keep that straight, but eventually, and it's correct in the notes, I think. So let's now go, instead of analyzing every possible, in the class notes, there's all sorts of stuff that I suggested that we skip, and we just go to section 3.7, which is the electroweak model, which in its present form, it was basically put forward by Weinberg in, I think, 1967, but I'm not sure. You could correct that. And I think for some time, nobody referred to it. I think it went 2 years without a reference. Anyway, the local gauge group now is SU2, and one calls it SU2 left cross U1. And we write it that way because this is a U1, maybe I should call it SU2 left, and the U1 is a U1 of hypercharge. And so maybe I should say something about what the hypercharge is and what left is. If you have a Dirac field, what you've got is psi 1, psi 2, psi 3, psi 4. The upper two are the left field. So this is psi left and psi right. The gauge transformation only acts on the upper two components. The hypercharge acts, it's a U1, and so it acts on psi 1 and psi 2 equally, and it acts on psi 3 and psi 4 equally, but it acts on the right-handed ones, it acts on psi right differently from the way it acts on psi left. In fact, I think what I'll do is write down for you what these numbers are. So we have left-handed leptons, so nu left and E left, and this is sort of nu E, nu mu left, nu tor left, tor left. All of these have y equals -1. Then we have the quarks, and we have up, we have charm, and we have top. Well, it's a T really. And we're talking left here. The left-handed, actually all the left-handed quarks have 1/3. So this is also true for down left, strange left, and bottom, bottom left, yes, 1/3. So everybody is, all the quarks have y equals 1/3. And this was left-handed. Now if we go to right-handed, so the left, and these numbers are reasonable. If this were the whole model, we'd say this was an attractive model. Now look at the right-handed ones. The up quarks have so U right, Chaume right, top right, they have y equals -2. Y. The right-handed down quarks have, the value is 4/3. I'm sorry, I was reading the wrong line here. You should have these numbers memorized, but I actually don't like this picture very much. So right-handed up quarks, 4/3. Right-handed down quarks, -2/3. And the gauge bosons all have y equals 0. So W, Z, photon, y equals 0. And what I left out was the Higgs, and the Higgs has y equal to 1, I think. I wrote that down, and I just want to make sure I have. God, I think I didn't write it down, but I think it's y. Yeah, y equals 1. So the Higgs So what we see here, I think, is that, I mean, the view most people have is, these are strange quantum numbers, but everything gets fixed at 10 to the 16 GeV, and that may be true. Remarkable thing is that this standard model actually works with amazing accuracy in all known experiments. The only departures are neutrino oscillations, and they can be sort of worked in. And in fact, what I should have said when I was talking about integrating over higher mass fields is that I think in his 1979 paper, Weinberg pointed out that if you did these sorts of integrations over high mass fields and insisted on various properties such as gauge invariance, whereas I was just looking at Lorentz invariance, but if you include gauge invariance, there's only one term that is allowed, and that's a lepton doublet, a Higgs field squared over a mass. And the other ones have higher powers of mass here. And this turns out to give a Majorana mass to the neutrinos. And moreover, it gives a small Majorana mass because M is huge.
Where's the Majorana mass?
Well, you remember that if you have a left-handed field, let's just call it nu, under a Lorentz transformation, it goes as e to the z dot sigma.
Okay.
Now, if you take the transpose of that and do e to the z dot sigma transpose, that's actually invariant. Now, let's see why it's invariant. The reason is that this is nu transpose. Let me see now. I'm not seeing this being invariant, actually. The sigma 2 flips sign. Oh, sorry, we need to put in another matrix, sigma 2. And now, if we have the sigma 2 there, what happens is when you move this through, the sigma 2 has already flipped sign because it's antisymmetric. The sigma 1 and sigma 3 flip sign when they move through the sigma 2 because they anti-commute with it. So this is e to the minus d dot sigma, e to the z dot sigma nu. Why do I have, this is sigma 2. So this is nu transpose sigma 2 nu. So in other words, this structure, nu transpose sigma 2 nu, is Lorentz invariant. And it's Lorentz invariant whether this is nu left or nu right. If it's, and the difference is, if it were nu right, it would be z star dot sigma. But obviously the z star doesn't make any difference. It's all has to do with the sigmas. Okay. So these things are, if you multiply by an m, these things are called Majorana masses. And there's a great mystery that Majorana was an Italian theoretical physicist who, as far as I know, disappeared at some point. And do you know the story?
No, I don't know. I mean, I've heard of this though. That this guy.
I'd love to. If any of you finds out what actually happened to him, or what the best story is,
yeah.
The most accurate version, or what is known, I'd love to hear about it.
Yeah. So I was going to ask these Dirac fields that only have a left-handed part or only have a right-handed part, are they indeed Majorana fields in the sense that they're their own antiparticle fields? Or
Well,
this idea that I remember last.
One of the troubles is that names occur in science as soon as something is discovered. And then 10 or 20 years when the thing is understood, the name is often inappropriate.
Yeah, I see.
Now, it's perfectly fine to honor Majorana with any phenomenon. This is called a Majorana mass term, and it's a mass term in which, in fact, in a certain sense, the only mass term is a Majorana mass term. The difference is that in the case of a Dirac mass term, what you have is you have two Majorana fields, and you take a complex linear combination, and that's your mass, that's your field, and so what you have is a complex Majorana mass term. So let me first of all point out something that's weird about this. This term or this term, it's nu transpose, so this has an annihilation operator for a neutrino. This also has an annihilation operator for the same neutrino. What's funny is the spinner is on the side or something. But it's the same annihilation operator. So this doesn't conserve lepton number. Now, if this were charged fermion, this would be crazy because this would violate charge conservation.
Sure.
But because the neutrino is neutral, it doesn't violate charge conservation. So there's the possibility of having these terms. These are Majorana mass terms. And the Majorana spinner could be left or right. Now what you have over here is a Dirac field, and in my way of, the way I talk about physics or Dirac fields is that a Dirac field is just something that has 4 components. And what you can have is you can have a field psi. In fact, we could have a field psi nu that was nu left and nu right, in which this thing, both were Majorana. Now, I'm using the word Majorana differently now, damn it. So, let's suppose simply that this is a neutral field, so that you could make a Majorana mass term from it.
Okay.
So, you could have phi 1 is nu 1 left, nu 1 right. Now, if these fields were massless, then you could have, you might have another field, nu 2 left, nu 2 right, and if they were both massless or both had the same mass, you could then make a thing called psi, which is psi 1 plus I psi 2. I'm leaving out square root of 2's for simplicity. And so this is nu 1 left plus I nu 2 left, and this is nu 1 right plus I nu 2 right. So you take a complex combination of these things, and now, and this is what a Dirac field is. So in other words, you can think of, there are 2 senses of Majorana. There's Majorana mass, which is like this, and only is possible for a neutral field. Then you can talk about a Majorana field. That's a field that's neutral. That's a field that's well, it's just a single field. Well, you see, if you have just a single field, the issue of charge doesn't arise. Charge arises only when you have 2 fields of the same mass. You take a complex linear combination, and then you can have the possibility of charge, because charge is a U1 rotation. So you can think of a 4-component Majorana field. I don't know, in my book I think of a 4-component field as a Dirac field. So my use of language is totally confused. And I'm totally confused. The mathematics I understand, but I think, but the words are hard to. It's not as bad as astronomy, though. All right, so other. Anyway, so what Weinberg did back in '79 was he pointed out that if you looked at integrating over heavy fields, the only gauge invariant term was this one, and that explains why the neutrino masses are light. Because back in '79, I don't know if one was even sure that there were neutrino masses. I think Ray Davis had shown that he was getting only 1/3 of the number of neutrinos from the sun that solar theorists like, I think it was McCall at Princeton, predicted. And that went on for some time. I mean, there were decades when people, there was at least a period of 20 or 30 years when people weren't sure whether neutrinos had mass or not. Of course, before that, they weren't sure either, but they just took for granted they were massless. Most people did. And in the standard model, the technically defined minimal standard model, they are massless. And anyway, we know now that at least there are at least 2 of them that are massive, and probably all of them, and possibly 6 of them, because I think, in fact, that because of this SU2 cross U1 symmetry that rotates neutrinos into electrons.
Yeah,
and
but that's
so
a supersymmetric. I mean, so
Huh?
the 6 neutrinos, the 3 additional neutrinos, those are supersymmetric neutrinos?
No, not supersymmetry. Forget supersymmetry. No. What I think is this, that you're rotating neutral leptons into charged leptons. If you're doing that, then the neutral leptons, I think, have to be the same as, have to have the same structure as the charged leptons. The charged leptons are complex, and so I think the neutrinos also have to be complex. So in other words, they're direct neutrinos. When you look at them before symmetry break-in, when everything is massless. On the other hand, after symmetry breaking, there are at least two possibilities. One is that the neutrinos get very small masses and they're Dirac fields, which means that they're linear combinations of 2 fields with exactly the same mass. In other words, two component Majorana fields, linear combination, same mass, or the masses could be different. And in that case, the neutrinos that we've seen experimentally that have small masses could be Majorana neutrinos with small masses. And the other degree of freedom could be very heavy masses. Could be neutrinos of very heavy mass. And, or moderate mass. I mean, we don't know. So there's a lot of mystery there. But the fact that Weinberg did this back in '79, 12 years after inventing the Standard Model, I mean, he's clearly he stands out as being the top line after Einstein, I would say. Well, Whitman, of course, is very smart also. There are a lot of very smart people. All right, anyway, here's the rotation. We have a gauge field. The Higgs field transforms this way. The gauge field transforms this way. All right, I started writing incorrectly, so I wasn't looking at my notes. It's unitary, so it doesn't matter. Now, what's U of X? Well, U of X here is IG sigma A over 2. Well, that's an exponential. Well, yeah, this was stupid. EXP. Yeah, I forgot the EXP, so this is wrong in the notes, actually. So I have the square bracket, but I left out EXP. IG sigma A, say alpha A of X, plus I G prime Y I over 2 beta of X. So this is the SU2, this is it, the SU2 left cross U1 hypercharge transformation.
What was H?
Huh?
Sorry, what is
H is the Higgs field. H
Okay. Oh, yeah.
is H plus H0.
Yes.
It will turn out that before symmetry breaking, it's a field that is positive and negative, and then 2 neutral fields. So the action of the theory is d mu h dagger, I'm now using the Greek letters, d mu h plus 1 over 4k trace f mu nu plus m squared h here h squared is h dagger h. So h is a two-component complex field. D mu h is the identity times the derivative plus I G, a coupling constant, a Pauli matrix over 2, the eighth gauge field, A mu, plus I, another coupling constant, Y, I over 2, B mu, H. So H is two complex scalar fields. B mu is a vector field. Y is has a different value for each doublet of, well, for each, I should say, it has a different value for different, has different values for different fields, and it's those are the numbers that I wrote down over there. And these A's are the gauge fields for SU2 left, and this is the gauge field for U1 of hypercharge. And once again, the minimum, if you said 0 is the partial derivative with respect to absolute value of h squared, you set that equal to 0, you get 2 lambda h squared minus m squared. And so that just tells you that h is m over square root of 2 lambda. And we then call this v over square root of 2. And the idea here is that H0, which is to say the Higgs field in the vacuum, is 1 over square root of 2, 0v, where v is real. So this is the convention to, you factor out the square root of 2 and you have a v here. These square root of 2's are because the standard thing for a real field is 1/2 times the mass squared times the field squared, 1/2 times the gradient squared of the field, and so forth. There's always a 1/2. When you write down complex fields, you leave out the 1/2, so you sneak it back in by defining the complex field as 1 over square root of 2 real plus imaginary, plus I times the 1 over square root of 2, one field plus I times the other field. I don't know, it's, somebody should come in and clean up this notation. I suppose in 100 years this will be written in a nicer way. So this is what the potential looks as a function of V, and V double prime at V is the mass of the Higgs squared, the physical mass squared, and that is square root of 2 times the mass parameter m, and that mass parameter is square root of 2 lambda times V. And experiments first, once again, this was the Europeans at CERN, at LEP 2, who determined that V was 246 GeV. actually, I don't know, there were American experiments at SLAC where once again they had an electron-positron collider, and so they could see what was happening. And in 2012, the Large Hadron Collider showed that the mass of the Higgs was actually 125 GeV, and the coupling constant lambda, therefore, is 0.129. This is mh squared divided by 2v squared. Okay, so now we're looking at the mass terms for the gauge fields. And so how do we get there? We go to the kinetic part of the Higgs field. We use the definition of the covariant derivative, and then we essentially we set the Higgs field equal to its vacuum value, so we drop the small terms. We basically set the Higgs field equal to this, 1 over root 2, 0v. And when we do that, what we have is this, minus a half 0v g sigma a over 2 a mu plus I g prime. We know what the hypercharge of the Higgs field is +1, so this is just I over 2 b mu times g sigma a over 2 a mu, say, plus g prime I over 2 b mu, and all that times 0v. And here I've pulled out, there was presumably an I here and a minus I there, so they just come to 1. And there was a 1 over square root of 2 in the definition of the Higgs field. They came out from here and here and reduced this 1/2. By the way, if you are sick, the best thing is to cough into your elbow. Yeah. Thanks. Okay, if we work this out, this is just matrix algebra, so this becomes 1/8 0v. And this structure here, these are 2 by 2 matrices. What you wind up with is this. GA3 mu plus G prime B mu. This, of course, is in the class notes, page 34. G A1 mu plus I A2 mu. G A1 mu minus I A2 mu. Minus G A3 mu plus G prime B mu. That's the first matrix. The second matrix is G A3 mu plus G prime B mu. G A1 mu plus I A2 mu. G A1 mu minus I A2 mu minus G A3 mu plus G prime B mu, and then this is acting on 0v. Well, if you multiply that out, I'm going to skip one line because it's late. What you get is minus v squared over 8 g squared times A1 mu plus, plus A2 mu plus minus G A3 mu plus G prime V mu. Well, this, I mean, you could say that this is squared. All I'm doing here is raising the Lorentz index. So that's what those are the mass terms. And what this tells you then is that the field A1 gets a mass, the field A2 gets a mass. They're the same mass, basically GV. And then one linear combination of the A3 and the B gets a mass. And the other one that's orthogonal is left out, so it has mass 0. That's the photon. And so that, what we've gone through today, I think, is the nicest part of the standard model, because these mass terms have come because we required that the action be gauge invariant, and so the derivative on the Higgs field is covariant. So it has these gauge fields which act as shock absorbers and compensate for the local, make the local gauge invariance possible. And then the other thing that I find really quite magical is that this field that's been hanging around since men could see, that is to say, the photons enter the retina and we see. This field, now we realize, is actually a linear combination of two fundamental gauge bosons. And so that's quite, I think, interesting. So let me just say a little more to straighten things out, what these things actually are. So the mass states a W plus and minus mu, which is 1 over root 2, A1 mu, and it turned out to be minus or plus I, A2 mu, and the massive state is called the Z, and Z is 1, you want to normalize it correctly, G squared plus G prime squared, G A3 mu minus G prime V mu. So it's, apart from a minus sign that you, obviously this thing is squared, so you can put in a minus sign, doesn't make any difference. You put in the minus sign and then you get something, and what you want is you want this sort of normalization because you want the sum of the squares to be unity. Just as over here you have 1 over square root of 2 squared is a half plus 1 over square root of 2 squared is a half. That adds up to 1, so here you have G squared over the square root plus G prime squared over the square root gives you 1. And in terms of these normalized fields, these mass terms are minus G squared V squared over 4, W minus mu, W plus mu, minus G squared plus G prime squared, V squared over 8, Z mu, Z mu. And so the mass of the W, now you could predict it from knowing what lambda and V are. Well, you have to know what G is, so hold on just a second. This is then GV over 2, and it turns out it's 80.385 GV over C squared, and the mass of the Z the square root of g squared plus g prime squared v over 2, and that's now 91.1876 GeV over c squared. The orthogonal major boson is the photon, and that's a mu 1 over the square root of g squared plus g prime squared, and it's g prime a 3 mu plus gp mu.
I think you have the primes on the other side on. Oh wait, no, but you factored out the square root. Never mind.
And then, of course, you can, well, let's see, we're out of time, but on page 35, I do the obvious thing of writing the three A's and the B in terms of the mass eigenstates W, Z, and the photon. So
Yeah, actually, sorry. I don't know. Is this a mistake or not? That here
let me give you guys some more candy.
in your expression for A mu.
What now?
In your expression for A mu here,
Yeah.
you have the G prime on your A mu 3.
Yeah.
Whereas in your expression with these matrices, you have the G prime on the B mu. And you also have
Over
the G
here.
prime. Yeah, well, and even up in the matrices above.
Yeah. But that's right. But we
switches,
want
yeah.
the photon to be orthogonal to this. This is the Z.
Ah.
This is the
I see,
Z.
I see.
So the orthogonal combination is that. And the
Okay.
Z is this one, which is the one that's over there.
Yeah, it's okay. I get you.
Perhaps I
So
should have waited to walk out.
What?
And maybe this was asked, but where does gravity, does gravity end up this way, or do you have to add gravity in a different way?
Oh, we don't have gravity at all yet. For gravity, gravity is a whole different thing. I've got in the class notes the part on effective quantum field theory, which is the integrating over high mass fields. After that, I describe some things about gravity. But the best place to... I describe classical gravity in the online notes on... I mean, I cover that in the chapter on tensors in my book, classical gravity.
Yep.
Now, what we might do in this course is consider how to quantize ordinary fields in curved space-time. You think that's interesting?
Yeah.
Sure. Yeah.
All right. I think that's worth looking at also. All right, so we can turn this video thing off, I think.